Download this code from codegive.com, link in the description below. Concurrency in Swift 5.5 with actors, async/await, and data race prevention. Swift 5.5 introduced significant enhancements to concurrency, making it easier to write safer and more performant asynchronous code. This tutorial will delve into the concepts of actors, async/await, and data race prevention in Swift, providing practical code examples and explanations. 1. The problem, concurrency and data races. Concurrency allows multiple parts of your program to run seemingly simultaneously. This can greatly improve performance, especially on multi-core devices. However, concurrency introduces the risk of data races. A data race occurs when multiple threads access and modify the same memory location, variable or property, concurrently, and at least one of them is writing. This can lead to unpredictable and incorrect behavior because the order of operations is not guaranteed. Example of a data race, illustrative, don't run this. In this example, multiple threads might simultaneously try to increment count, leading to missed increments and an inaccurate final value. The dispatch queue.concurrent perform queues tasks to run concurrently on multiple threads. The problem lies in that the increment function isn't thread safe. 2. Traditional solutions, and their drawbacks. Locks. Historically, developers used locks, mutexes, semaphores, to protect shared resources from concurrent access. While locks can prevent data races, they introduce several drawbacks. Complexity. Using locks correctly can be complex. You need to acquire a lock before accessing the shared resource and release it afterward. Forgetting to release a lock can lead to deadlocks. Deadlocks. Two or more threads can become blocked indefinitely, waiting for each other to release locks. Priority inversion. A high priority thread can be blocked waiting for a low priority thread to release a lock, leading to performance issues. Error prone. Manual lock management requires careful coding and can be difficult to reason about. 3. The Swift solution, actors. Swift's actor provides a more structured and safer way to handle concurrency. Actors are a type of class that encapsulates state, properties, and behavior, methods, and isolates that state. Only one thread can execute code inside an actor at any given time. This serialization of access eliminates data races. Key concepts of actors. Isolation. Actors isolate their internal state. Only the actor itself can directly access its properties. Serialization. Code within an actor runs serially. Only one method or property access can be active at any given time. Asynchronous messages. Interaction with an actor from outside is always asynchronous. You use await to suspend execution until the actor is ready to respond. Non-isolated. You can mark some methods and properties as non-isolated. These can be accessed synchronously from outside the actor, but only if they don't access any isolated state within the actor. This is useful for read-only access or purely computational methods. Actor example. Explanation. One actor safe counter. We declare an actor named safe counter. 2. Private var count. The count property is private and can only be accessed within the actor. 3. Func increment, and func get value. These methods are part of the actor's interface. 4. Await counter. Increment. When calling increment from outside the actor, we use await. This suspends the current execution until the actor is ready to execute the increment method. The await keyword signals that this point may be a suspension point where other code can run. 5. Task. **** We wrap the code that uses the actor in a task. This creates an asynchronous context that is required for await to work. Task is the basic unit of concurrency in Swift's structured concurrency system. 6. Await with task group ***. This allows us to create a group of tasks that run concurrently. The code inside the add task closure will be executed concurrently, subject to the actor's serial execution constraint. Await group. Wait for all suspends the current task until all tasks in the group have completed. This ensures that all increments have finished before reading the final value. 7. Await counter. Get value, ***. We also need to await the call to get value. Since get value is a method of the actor, accessing it from outside the actor requires asynchronous messaging. Why this is safe? No data races. The Swift compiler enforces that only one thread can execute code within an actor at a time. This serialization of access eliminates data races on the actor's internal state. Clear syntax. Await makes it clear when you're interacting with an actor and potentially suspending execution. Compiler enforcement. The compiler provides strong guarantees about actor isolation, helping you write correct concurrent code. 4. Async/await, making asynchronous code easier to read. Async/await is a language feature that simplifies asynchronous code. It allows you to write asynchronous code that looks and behaves like synchronous code. Async functions. A function marked with async can suspend its execution at certain points, marked by await, to allow other code to run. These functions perform asynchronous operations. Await keyword. The await keyword is used to wait for the result of an async function. When the await keyword is encountered, the current function's execution is suspended until the awaited function completes. During this suspension, other tasks can run. Once the awaited function returns a result, the original function resumes execution from the point where it was suspended. Example of async/await, simplified. Explanation. 1. Async throws -data *. The fetch data function is marked with async because it performs an asynchronous operation, network request. It also throws because network requests can fail. 2. Try await URL session.shared.data, from, URL, *. We use await to wait for the result of the data, from method, which is also an asynchronous function. 3. Task. *. We use a task to create an asynchronous context and handle potential errors with try. 5. Data races in actor code, ensuring complete isolation. While actors largely prevent data races on their internal state, it's crucial to understand how to maintain isolation when interacting with data from outside the actor. Scenario: sharing mutable data with an actor. If an actor interacts with mutable data that is also being accessed from outside the actor, you still need to be careful to avoid data races. Bad example: potential data race. Why this is bad? The problem here is that shared data.value is being modified both within the data processor actor and directly within task 2. Even though data processor protects its internal state, it doesn't protect data that's passed in from outside that's being concurrently modified elsewhere. This creates a data race. Solution: encapsulation and copying. The best solution is to encapsulate the mutable data within an actor or to copy the data before passing it to the actor. Good example: data encapsulation within an actor. Explanation: 1. We created a new actor, data container, to encapsulate the value property. 2. The increment method is now part of the data container actor, and all modifications to value happen within the actor. 3. The getValue method is also part of the actor, ensuring that access to the value is serialized. 4 tasks only interact with the data through the actor's methods, preventing data races. Another solution, copying. If you cannot encapsulate the data within an actor, you can copy the data before passing it to the actor. This ensures that the actor is working with its own copy of the data and cannot interfere with the original data. This approach works best with value types like structs. For reference types, you would typically create a deep copy. Explanation of copying method asterisk. 1 value type, struct. We use a struct, value type, for immutable data. This is crucial because when you pass a struct to the processed data function, a copy of the struct is made. 2 immutable data asterisk. We ensure the value property within the immutable data struct is immutable using let so that we don't accidentally mutate it within our tasks, though it can be reassigned by the result of the actor processing. 3 actor processing asterisk. The processed data method receives a copy of the immutable data. It performs its processing on that copy and returns a new immutable data struct. 4 assignment asterisk. Outside the actor, in each task, we reassign shared data with the result of the processed data method. This means we're effectively replacing the original shared data with a new shared data that contains the updated value. Important considerations for copying asterisk. Asterisk performance asterisk. Copying can be expensive, especially for large objects. Consider the performance implications. Asterisk deep copying asterisk. If you are dealing with a reference type, class instance, you'll need to perform a deep copy to create a completely independent copy. Deep copying can be more complex than simply assigning a new value, as you need to recursively copy all nested objects. You might use nskedarchiver and nskedunarchiver to serialize and deserialize an object for deep copying or implement the copy with method when adopting the NS copying protocol. Asterisk struct immutability asterisk. Structures in Swift are value types, so assignments create copies. The let keyword ensures that value within the struct itself doesn't mutate but is reassigned from the return value of await processor. Processed data. Asterisk copy on write optimization asterisk. Swift's copy on write optimization can help reduce the performance overhead of copying structs, especially when they are not modified frequently. However, this optimization can be bypassed if mutation is detected. 6. Non-isolated keyword, save synchronous access. The non-isolated keyword allows you to mark certain methods and properties of an actor as not requiring isolation. This means they can be accessed synchronously from outside the actor, without using await. However, there are strict rules. Asterisk no access to isolated state asterisk. A non-isolated method or property cannot access any of the actor's internal, isolated state, i.e., any var or let property that is not also non-isolated. Asterisk read-only or purely computational asterisk. Non-isolated methods are typically read-only or purely computational, they don't change the actor's state. Example asterisk. Use cases for non-isolated asterisk. Asterisk read-only properties asterisk provides synchronous access to read-only properties that don't affect the actor's state, like a unique identifier. Asterisk utility methods asterisk implement purely computational helper methods that don't rely on the actor's internal state. Asterisk improving performance asterisk reduce the overhead of asynchronous messaging for operations that don't require isolation. 7. Summary and best practices. Asterisk use actors asterisk whenever you need to manage shared mutable state in a concurrent environment, use actors. They provide a safe and structured way to prevent data races. Asterisk understand async/await asterisk use async/await to write more readable and maintainable asynchronous code. Be mindful of data races outside actors. Pay attention to data that is passed to actors and ensure it's either immutable or copied to prevent data races outside the actor. Encapsulate state. Ideally, encapsulate all mutable state within actors. Consider value types. When possible, use value types, structs and enums, to simplify concurrency. Value types are copied when passed around, making it easier to reason about data ownership. Use non-isolated judiciously. Use non-isolated only when you're certain that the method or property doesn't access isolated state and doesn't introduce concurrency issues. It offers a performance advantage, but at the cost of stricter limitations. Thorough testing. Test your concurrent code thoroughly to identify and address any potential data races or concurrency issues. 8. Advanced topics, briefly mentioned. Actor reentrancy. Actors can re-enter themselves during asynchronous calls. Be aware of this possibility and design your actors accordingly. Actor isolation in UI frameworks. Swift UI, UIKit. UI frameworks often have their own concurrency models. Swift actors can be used alongside these models, but you need to understand how to bridge the gap between them. For example, updating UI elements from an actor typically requires dispatching to the main thread. Global actors. Swift provides global actors like @main_actor and @background_actor, which are predefined actors that execute code on specific threads or queues. These are useful for integrating with existing systems or managing specific types of concurrency tasks. By understanding and applying these concepts, you can write safer, more efficient, and more maintainable concurrent code in Swift using actors, async/await, and best practices for data race prevention. Remember that concurrency can be challenging, so careful design, thorough testing, and a good understanding of the underlying principles are essential.